Any questions or comments up to now? Uh, so last class we took a look at a few reversible processes involving ideal gases, and so I think those are also discussed in the text. So everything should be straightforward. Okay, so today I want to begin lectures on entropy. Okay, so and I want to introduce why entropy is needed, or the the thing that it causes, that is quite a thing that leads to wonderment in our real world. Okay, and I'm going to use a very simple example, and that is this idea that we've already seen in the joule-free expansion, but I'm just going to use the experiment itself. And so if you have a gas, and so this is motivation here, or at least one. It's not the only way to get you to think about things, but it's one way. It's actually quite awe-inspiring, or it's really one of those things that makes you go, hmm. Okay, so gas. So if you have a gas, right? Say, remember in the joule-free expansion, we had a container. It was insulated. So it was insulated. Okay, so we had a gas and it's insulated, and we assumed that this was ideal so that there is no heat interaction. Okay, so we assume ideal, so there's no heat interaction. And the other thing that was implicit, we had gas initially on this side, and we had a vacuum on this side, means zero pressure. P external is zero. Okay, so there's nothing there. There's nothing there. And here's a partition. Okay. Here's a partition. And we said what was implicit, and I didn't say this explicitly, but I hope it was implicitly understood, that the container is rigid, a rigid container. So there is no, apart from when you remove the partition, which I think people anticipate I'm going to do, apart from removing that partition, there is no other source of volume change in the system. Okay, so the container is rigid, so that the container, we call everything that's surrounded by this insulation, so that initially includes the gas part and the vacuum part. That's your whole container, and all of those boundaries are rigid. Okay. Okay. And our system is the gas. Okay. So and in the experiment, we say that by removing a partition, we can remove the partition in such a manner that it doesn't perturb the system in any way. So we're not going to um, just, we will propose the experiment, right? Because we can, as a model, so that there is no effect on the gas by removing the partition. So you might say, well, oh, what about all the particles right next to the wall? And maybe by pulling out the partition, you create friction. And then whatever friction you get on those particles is sort of translated to all of the other particles down away from the wall. But what we're going to do is say that none of those effects are important. Okay, we just pull the thing out. It's simple, and we one of the few cases where we can be mindless. So it's a very simple experiment that we're going to pull the partition out. And if we pull the partition out, okay, what happens at the end is that we have gas now all over, and of course the insulation is still there. But now all of the gas particles are dispersed, and I'm just going to label them as particles. It doesn't really matter, right? We can call them molecules if you want, but we're talking about an abstract principle here. So we have this arrangement, and of course n is the same in both cases. though I may not have shown the same number of particles in each case, but it's okay. So, okay, so the thing, there are a few things here. One can ask, well, once I remove this partition, once I remove that partition, okay, why is it that all the molecules seem to move to fill that volume? And if you stop to think about it, if you stop to think about it, okay, there's no reason for that gas to instantaneously move into that empty region, right? We said that there's no heat interaction because the thing is insulated, that whole assembly. And once we remove that partition and we assume that there's no effect of removing that partition on any of the particles of the gas, well, one logically, right? And it's very reasonable to say, well, wait a second, why would the gas go there? Right? Why? What is driving it to be there? Now, if you have a gas or a liquid in a conduit, a pipe, like in your home, the thing that drives that fluid to the second floor is a pressure difference. You have a pump. You have something that's external to the system. If you take the water, for instance, as your system, there's some pump that's external to that system that causes it to move. So in that sense, we have a very palpable thing that says, oh, okay, well, that's why this thing moves from the first floor to wherever your water is to the second floor, if you want to take a shower. But in this case, and this is an experiment that you can do in the lab, you've already done it probably. Why does the gas move? And this is something that a child would ask. Okay, I mean, and it's okay because any logical person would ask that. Why does the gas move? Right? There's no ostensible reason for it to move. Okay? It's almost an isolated system once you remove that partition. So if you have an isolated system, there's nothing acting on it. So another way to think about this motivating question or idea is that once you remove that partition, and we said that we remove the partition without any perturbation of the gas, right? So it's almost as though we're saying that, all right, I want to have a system that the initial instant of time, it's all on one side. It's all on one side, okay? So that's what we're doing really, is we're starting with the system artificially created to be on one side, the gas molecules, and then we're going to see what happens when you have this isolated system, half of which, it doesn't have to be half, but part of which has gas on one side and the other part has no gas on that side. Again, I reiterate, because this is kind of important, and I want you to sort of get some wonderment out of this, is that why does it move to the empty region? Why? It's an isolated system. They have no driving force for doing that. But it happens. It happens. This is what we see. This is real. Okay? So we need to explain it. We need to sort of reconcile this logical dilemma. Okay? And it's a very natural logical dilemma. Okay? A young child would ask this, well, why does it move? Why does it go there? So that's what we want. That's one of the things I want to motivate hereby. And so we need to have a driving force. So what is the driving force? And by force, I'm using quotes again here because force is a word that you can use in many, many ways and in many, many instances without really understanding what that word means, okay? And so in this case, I'm going to use this word in quotes and we will see what that driving force is more specifically and more explicitly as we continue our discussion of entropy, okay? One of the things we always have to be careful about, even us adults or us old people who do this for many decades, is we use words sometimes which words are ambiguous. And so we have to be very careful. Okay, so what is the driving force? We need to understand that. And so this little experiment motivates that. The other thing that I want to emphasize about this experiment is this, okay? And this is another thing that should cause wonderment if you really think about it. And these simple things cause a lot of wonder. Physical laws And by this, I mean things like Newton's laws of motion. Okay, Newton's laws of motion really is just F vector is equal to mass times A vector if you have a particle. Okay, and a very fundamental notion of physics is that the laws of physics that govern our universe as we know it today, they're time reversible, or they have what is called time symmetry, time reversal symmetry. So the physical laws that we have currently, or we know about, are time reversible. Okay, they're called time reversible, or it's called time reversible symmetry. Now, you can symmetry. You can talk about this on and on and on. Okay, but for now we'll just let it be this. And by time reversible symmetry, what I mean is that, let's say in our system here of gas particles, okay, right? If you were to look at the system here of particles after you remove the partition, right? We know that if you have T not equal to 0, okay, temperature is not equal to 0, and obviously that was the case in that experiment. All of these particles, apart from having a position at any given instant of time, so at any instant of time, all particles have a position. Okay, but they also have a velocity. And we can go dot, dot, dot. They have a velocity. And that's a vector. So the velocity you can represent, I'll just write all of these guys. So these are the velocities. So this is the velocity of particle 1. This is the velocity of particle 2. This is the velocity of particle 3, and so on. Okay, and so the arrows give you the direction. And for the moment, we don't have to worry about the magnitudes. I'm just concerned about the direction. Okay, so let's say I start at some instant of time. I had a camera. Okay, I had a movie camera, a very sophisticated movie camera. Again, I don't, but let's assume I do. And I were to be able to capture on this movie, this camera, each and every particle in this box. Okay, and in real time, I would be able to take a movie of all of these particles moving around. Okay, let's just assume we have this kind of instrument. We don't, we're going to assume it. So all of these particles, then we capture the movie, okay, of these particles, and it doesn't matter when we start the movie, we just started at some time. The system is at equilibrium, okay, the system is at equilibrium, so it's been there for a while, okay. And so we take a movie, and it doesn't matter how long the movie is, it's a movie. And so now you go back, take a look at the movie, right? You start at time t equals 0, which is whatever time you started the movie filming, and then you'll see all the molecules moving around, each and every one, okay? And now you do this little trick, okay? Now you do this little trick, okay? Because we can do this nowadays with the technology that we have. You take the movie, all right, and you play it all the way to the end, right? And you stop it at the end, right? Now you go to your buddy, right? And you show him the movie. You say, hey, look, I got this really cool movie. I made up this video cam. I can take movies of particles, of molecules. So I want to show it to you. Okay. So what you do now is you have your movie that you started at time t equals 0, but you actually stopped it after you watched it at some future time, t equals t future, right? So it's at the end of your movie. And what you do with your buddy is that you play it backwards. You play the movie backwards. Okay, so you start at time t equals t future meaning the end of time that you stop recording, and you play it to the beginning, and you show your buddy, and your buddy says, wow, that's really cool, right? He's not going to say, well, wait a second, it looks like it's backwards. Well, he's not going to, or he or she is not going to say that. And this is what we mean by time reversal symmetry. the laws of physics that we understand, whether they're classical physics or quantum physics, are time reversible. And this is something that is so fundamental in our physical laws. And it's so taken for granted, but it causes a lot of wonderment. So if you were to take that movie and play it backwards, okay, if you were to play that movie backwards, show your buddy, they wouldn't think twice about it, not knowing how you took that movie. They would just assume, oh, okay, well, it's just, you're showing it to me from the beginning to the end in real time as it happened. But in fact, then you tell your buddy, haha, it's actually backwards. And then your buddy would be like, oh, really? Huh, interesting. Why is that? Okay, so this is the time reversal symmetry of the laws of physics as we understand them currently, based on what human brains have led us to over the centuries, and most recently the recent century, where we learned a lot. Okay, so given that the laws of physics have time reversal symmetry, one can ask, again in wonderment, is that, well, all right, I started this experiment with this configuration where I had all of the gas particles on the left-hand side of this container. And remember now, we made this experiment very, very carefully, such that by removing this partition very quickly, we said, and without any perturbation to the gas molecules, that system at the moment we want to consider the experiment, it's as though all of the gas molecules, as they would like to be, are on the left, okay? Because the partition removal did not perturb anything, okay? So if we started with this initial condition, right, and we were to take a movie, we would see that, all right, well, this is what would happen. Okay? And based on my discussion of the time reversal symmetry of physical laws, right, all of these particles at the top state, from equilibrium state at the top, would have a velocity and they would be moving. And you could take a movie of this, right? And after some time, you would find that everything would arrive at the bottom scenario, where you have all of the gas particles now taking up the whole space of that container. They're still moving, and so you would still see them moving. But why is it that you can wait forever and ever and ever and ever and ever and ever and ever and ever? Okay. More evers and evers than there are stars in the universe. Why would you never see the reverse movie? So if I were to tell you, okay, I'm going to start with this guy, right? I'm going to start with this guy, and let's just wait a while. Why is it that I will never get to this guy? Why? Well, the laws of physics are time reversible. There's equal probability to go forward and backwards, right? I mean, if you were to look at a system at equilibrium, you couldn't tell whether the particles were moving backwards in time or forwards in time. F equals ma is time reversible. There's symmetry in time. However, if that's the case, then we should be able to see this box where the particles are dispersed over the whole volume. If the laws of physics are time reversible, then it should be apparent that I should be able to see, at least at some point, everything on one side of the box. Whether it's the left or the right, it doesn't matter. I just use this idea of coming back to the left, if everything is symmetric in time. Okay, so that's given the premise that everything is time reversible. This is what's going on here. There's got to be something here, right? And again, we're talking about a system that we've constructed to be isolated, okay? So there's only one direction in which things evolve. Even though the laws of physics are reversible in time, they're symmetric in time, okay? And that is true. This is reality. The laws of physics are reversible in time, okay? So this experiment is not saying that the laws of physics are not reversible in time. This is not what this experiment is saying. This experiment is saying is, wait a second, there's something we don't quite understand here yet. Okay, so the wonderment here is the laws of physics are time reversible. However, in this experiment, we only see one direction. We see something that is not reversible or asymmetric. Okay. So what is that? What is going on here? What is the driving force, once again, for this asymmetry in time? Okay. And this is what entropy is all about. This is what entropy is. This is what entropy is going to allow us to rationalize in a very, very precise, I repeat, precise way, not using words, but in fact equations that are very, very precise. Okay. So those 2 points, I think, lay the foundation for understanding the profundity of this concept of entropy. Okay, entropy, we sort of gloss over with words that are very ambiguous, but in fact, it is one of the most fundamental concepts in our physical world. And in fact, it actually derives from information. Okay, it's this loss or preservation of information. And not only does it span from classical physics and classical mechanics, it goes all the way down to quantum mechanics, where we can think about things that are called quantum entanglements, where things are entangled. Okay, and all of that is related to information and entropy. So I know I said a lot, but this is very important for an upper level class, and I want to give you, this is high level stuff that you're paying for, right? This is the stuff that's high level. It's that entropy is one of the most profound concepts that we have, and it's not about chaos or randomness. It's something much, much, much more deep. Okay? And these 2 points signify or lead us to think about that depth of what it is that entropy is allowing us to think about. Okay, that's sort of my motivation. I'm now going to move into the more, I hope it's not mundane for you, but often students think it's mundane. But now we're going to get into the nitty-gritty of getting to what entropy is. Okay, any questions on that discussion? That was my motivation. Or any comments that people want to add? Okay. Very well, then let's move on. And I'm going to take the tradition in chemistry curriculum is to take the historical approach to introduce entropy. So what I'm going to do is introduce entropy to you historically without really needing to know the particulate nature of matter, meaning particles, okay, that molecules, atoms, quarks, gluons, pions, whatever. We're just going to say that matter is this continuum, right? I don't need to know anything more about a glass of water except that it's this mushy, fluidy kind of a thing, okay? I don't need to know if there's atoms or particles there. That's the historical approach, because it was entropy arose out of this consideration of heat engines. How do we get the most work out of things called engines, okay? And then I'm going to give you after I introduce it in that manner, I will introduce you to entropy from the point of view of particles. Actually, now taking into account that we actually have 10 to the 23rd particles in a system, and how does entropy come out of that analysis, where we have to take into account, knowing that they're there, entropy has to come out somehow. Okay, it has to be related to all of those particles. So let's take a look at heat engines. This is the historical approach. Okay, so the guys like Carnot and Joule and Gibbs, they were looking at heat engines a long time ago, close to the mid to late 1800s. That's when things matured, because they were, this industrial revolution, and you needed to have ways to transport things and what have you. So there was a practical application. That's why it's engines, right? Engines are practical. So we're going to start with defining a process. Okay, so heat engines, they were associated with work. Okay, so far I hope everyone realizes that if I plot on a pressure volume diagram, okay, if I plot any cycle, okay, so any cycle, and by any cycle, I am going to equivalently mean cyclic process. Okay, so by cycle, I mean a cyclic process. It's the one and the same. How am I going to do this? Right here. Okay. Any cycle will deliver, if you run it the right way, okay, you can run a cycle in one way and you'll get work out. You can run the cycle in reverse and you will have to put work in. Okay? So any cycle, if you run it in the proper way, just like in your engine, in a car, right, it's run in a certain way so that you get work out. And it's obvious to you that there's work because you go from point A to point B in your car, and there's an engine in your car. So any cycle will deliver work if you run it in a particular direction. So we already saw this when we looked at a very simple cycle long time ago in this class. Now I don't remember. Let's see. Let's go this way, right? So here's a very simple cycle. And if you go from point 1 to 2 to 3 to 4, and then back to 1, work is not zero. Remember, work is not is path dependent. And this is a good thing about work, because it's because of the fact that work is path dependent, running a cycle allows us to get work out. And that is the beauty of work not being a state function or being path dependent. Okay, so if work is path dependent, in this case, we saw that the work is just whatever's inside here. Okay. If work is path dependent, then depending on the cycle or the path that we create, we can modify or modulate the amount of work. Just by choosing another cycle, I might be able to get a different amount of work, because remember, work is path dependent. Okay? So the fact that work is path dependent allows us to create thermodynamic cycles, which we embed in engines to get work out. And this is the art of race car driving, apart from making things lighter. It's a whole synergistic enterprise, right? Or the space shuttle or airplanes, right? Everyone contributes. But when it comes just to the prospect of getting work out, here you're looking at the engine, and you want to devise thermodynamic cycles that you would embed in the form of an engine, okay, to get the most work out, or in this case, be most efficient, okay? Because the other aspect of a cycle is that you need heat. You need to put some amount of energy in. And in the case of your car, that energy comes through gasoline. And so that's expensive, right? Gasoline, well, not right now. Gasoline is not very expensive, but depending on world economic and political factors, that energy can be very expensive. And so the impetus and the motivation to have very efficient engines. Okay, as long as you have to pay for something, you know that people want to optimize things and make them more efficient. So we're going to look at a cycle. We're going to look at a cycle on a pressure volume diagram. It's one of the most ideal, well, it is the ideal cycle. It is the ideal cycle, meaning it's the most efficient that was created as a theoretical construct to consider all other types of cycles or engines, okay? And that cycle is called the Carnot cycle, or it can be called a cyclic process, okay? So this is a very important cycle. It's a very it's idealized. Okay, we never realize this in the real world. Again, it's idealized. And we can show this cycle on a pressure volume diagram, and that's what I'm going to do now. Okay. So here's our pressure, here's our volume, and whatever units that are relevant for pressure and volume. Okay. And the cycle is composed of two types of processes for an ideal gas, and we've seen both of them. Okay, the last couple of lectures, I went through analyses of these two types of processes, and that's why I did so. And I think I indicated that I would use them when we discussed entropy. Okay? So this is idealized. And because it's idealized, let me just sort of make these points. These are very important points, okay? So all of the steps here, all of the stages in this cycle are reversible. And that's good because we saw that the reversible process is a special process. It has very special characteristics about it. So it's reversible. And in this cycle, the thing that's being used is an ideal gas. Remember, we looked at an ideal gas and how it changes. The ideal gas is undergoing these processes, that adiabatic process or that isothermal process. Remember, we discussed this in the last couple of lectures. So we have reversible processes. All of the stages are reversible, and our material or substance under consideration is an ideal gas. Okay, or a fluid that can be modeled using the ideal gas equation of state. Okay, so that's why it's idealized. And so these are the stages, okay? So the first, and it doesn't really matter, this thing is going to go in a cycle. So we'll start here at point 1. Okay, this is our point 1. And what we'll have as we go to point 2, okay, and we'll go in this direction, okay, is an isothermal process. So this will be isothermal. Therefore, T1 is equal to T2. Okay, so we're going to have a temperature at the point T1, equilibrium state T1, and we're going to have a temperature at equilibrium state 2. But this is an isothermal process, so the temperatures are going to be equal. Okay, so it's isothermal and reversible. Okay, so that's one stage. The next stage is going to be adiabatic and reversible. Okay, so this is why we looked at the isothermal reversible process for an ideal gas and the adiabatic reversible process for an ideal gas. And we know that the slope for that adiabat is going to be steeper. We discussed that. So I can make this a little bit steeper, and it goes to point 3. Okay, point 3 will have a temperature T3 because it's different. This is no longer an isotherm. Okay, so this is a adiabatic process, and it's of course an adiabatic expansion. So we will go in this direction. Okay, so this is adiabatic and reversible. Okay, and so this is going from T2, which is equal to T1, to a new temperature T3 in an adiabatic process. And again, another demonstration that if you have an adiabatic process, temperature changes. Okay, temperature is not the thing that is constant in an adiabatic process. dQ is 0. That's what defines an adiabatic process. Okay, now we're going to go to state 4, and we're just going to go now in reverse, if you will, but not quite reverse. We're going to have another isothermal reversible process, but that isothermal reversible process is going to be at a different temperature, and that different temperature will be T3. So what we're going to do, and this is, you know, the textbook has good pictures, so don't, you know, I just draw it, but okay, so that's going to take us to point 4, and point 4 is going to be at temperature T3 because this guy is isothermal and reversible. Okay, and it goes in this direction. Right? You see how this cycle is panning out now? Just as we did here for this square type of rectangle, right? We had a cycle, and we know that whatever's inside is work. We're going to get work out here too, because now we're going to complete the cycle for this Carnot process, where we go from 4 to 1. It's just that it's not a rectangle now. It has these adiabats and isotherms for an ideal gas, which we have discussed so far. So the final stage in this Carnot cycle, or this Carnot process, or Carnot engine, right, will be, let's see, what color should I use? I'll just use this one. Right, we'll go through this way. And this is going to be an adiabat. So this guy will be adiabatic. Once again, it's all reversible. All of the steps are reversible. That's why it's an idealized engine. It's the most efficient engine that we have constructed in our minds. Okay, like, you know, that saying, he's a legend in his own mind, right? Okay, so this is the Carnot cycle. So you have 4 stages. Okay, 2 of them are isothermal, 2 of them are adiabatic. Okay, and the 2 isothermal stages occur at different temperatures, T1 and T2. And in the way I have presented this process, T1 is greater than T2. And I will rationalize it because T1, which is the top isotherm, occurs at a higher pressure. And we know just from our thinking of ideal gases that when temperature is high, pressure is high, or when pressure is high, temperature is high, and when pressure goes lower, temperature goes lower. Therefore, T1 or T2, because they're equal, so we'll call it T1. T1 is greater than T3, and T3 is going to equal T4 because we have an isotherm along that bottom process as we go back, right? So we'll say that T1 is greater than T3, okay? By the same token, T2 is greater than T4, and you can make those inequalities. Okay, so we're going to define something now. I'm just going to say that T1 is T hot. Okay, so let's say T1 is equal to T hot, okay, because it's at the higher temperature, and I'm just going to label that as TH, T hot. And then T3, I'm going to label as T cold. And that's just going to be T sub C. I don't want to write all these things over and over, fewer letters. So we have a T hot and a T cold. Everyone with me so far? Anyone want to discuss or comment or criticize? Okay. I will continue then. I don't hear anything. Okay. Great, so this is the Carnot cycle. So we know then that the work is going to be represented by that area inside of that, that whatever shape you want to call it, okay? So I'm not gonna muddle the figure. I'm just gonna say that the work equals the area inside the cycle. Okay, I want to introduce 2 other things into the plot and I don't want to get it confusing. Although the textbook does a very good job. All right, so in that first isotherm, okay, so you have 2 adiabats. We don't have to worry about Q or heat interactions in those adiabats because they're adiabatic. We've said no Q. Okay, great. Makes our lives easier. But in the isothermal case, we can have Q. Okay, there is Q flow. And you can think about it this way, right? If you have a process like a chemical reaction that liberates heat, right? If it's an exothermic reaction, and if you want the temperature in your system to be constant, then you're going to have to pull out heat. There's going to have to be heat interaction. That's why if you have an isothermal process, you have to have heat flow. Otherwise, that temperature is going to change, right? And so this is why in this case, in the 2 isothermal cases, you're going to have heat interactions between your system, okay, which is the gas in this case, which is undergoing this cycle of expansion and contraction, right? The first 2 stages are expansions. The second 2 stages are contractions. So you have expansion, contraction, expansion. And again, this is what happens in your engine, in the cylinders. If you are an aficionado of cars, you know cars can have 4 cylinders, 6 cylinders, 8 cylinders. That corresponds to the liter, the displacement, the liters, right? People like big engines with a lot of displacement. But what that means is in the cylinders, as they go up and down, when you spark that gasoline, you have an expansion of the cylinder. That gives you the force, it's translated into moving the wheels. And then you have a compression. Again, that's another bit of force that moves the wheels. And so you have this compression, expansion in a real engine. That's embodied here in this cycle. The thing that we have to embody is the aspect of the gasoline. right? We're putting energy into the engine. So it must be that in this engine or this cycle, we need to be putting in energy. And that energy comes through the isothermal steps, as I indicated. And we will show that by here. Okay, so at this stage, we have something called Q hot. Okay, so we have some amount of heat that comes in through this isothermal step, and it's called Q sub H, Q hot. And I'm going to write that as QH now. And it's called Q sub hot because that heat enters the engine through at this temperature of T hot. Okay, so that upper curve is an isotherm where T1 is equal to T2 is equal to T hot. And so the heat that enters into the system, and heat has to enter the system. Why? Well, we have expansion. We have expansion of the gas. Volume is increasing, okay, along that process. And the only way volume is going to increase is if we add heat into the system, right? It's going to cause the system to expand. This is what we have. We know intuitively that's what happens when you heat things, they expand. Okay. All right. So that's Q hot. And I think everyone probably has already jumped to the next point about Q cold, where heat is extracted from the system in the second isothermal step here. And so here we're going to have heat leaving the system, and we're going to call that Q sub C for Q cold. And again, why does heat have to leave the system? Well, the gas is compressing, it's contracting. And the only way we know, well, not the only way, but we know that with a contraction in the gas or a volume change that goes to smaller volume, you lose heat, the thing cools. Okay, so we have loss of heat in that. So again, in terms of this engine, you have to put in Q hot at that higher temperature. That's like you using gasoline to generate heat through a spark. It sparks the system. You have this expansion, right, in the cylinder. And there are all these 4-stroke, 5-stroke types of engines. That's what we're talking about. So you have this expansion when you put in heat, but you also need to remove heat from the engine. And that's why you have things called cooling fluid and radiator. You need to extract whatever heat that is generated in the process. Okay? And that heat is really wasted heat. Okay? So you can already sort of see here, well, wait a second, I'm putting heat in, but I'm getting heat out. So I must have lost something somewhere along the way. Okay? I am getting work out because the work is that area. So the work is the area in that cycle. I'm putting heat in, okay? I'm putting heat in, Q hot. I'm getting work out, but wait a second, I'm also getting heat back out. Okay, so this is very important. I'm getting heat back out. It's not as though all of the heat that goes in comes out as work. I put some Q hot, right? Through that expensive gasoline, I put in some Q hot. I get some work out, but wait a second, I also still get some Q out. It's not as though there's nothing coming out. Okay, so everyone okay with the cycle and the points I just made?
Yeah.
Okay, I'm going to make one more point and then we'll go, and we're going to apply the first law. Okay, and this is very quick, right? We know that the first law is du is equal to dq plus dw. Okay, and if we integrate this over any kind of a process, we know that we would get delta u, right? Integrating over a cycle. We're going to integrate over a cycle, and I'm going to indicate that by this kind of a thing. That's just going to give me q plus w, okay, over the whole cycle. But since this is a cycle, what can we say about delta u? Because u is a state function, delta u is just going to be
0.
0, right? And then q, well, how many q's do we have in here? Well, we have a q hot and a q cold, a qh and a qc. And we know with our sign convention that when the heat is put into the system, it's positive, and when it comes out of the system, is negative. Q sub c is coming out, so it's a negative. And Q hot is going in, so it's going to be a positive. But we're not going to worry about that at the moment. I just want you to keep that in mind. So this is just going to be Q hot plus Q cold plus W. And this is going to be the area in the curve. Okay. So we see here then that W is equal to minus Q hot plus Q cold. I'm just going to do algebra there. Okay. Now, is that okay? Finally, what I'm going to do is define something called epsilon, and then we're done. This is the Carnot efficiency. Remember how I was talking about efficiencies, because that's really important. This is the Carnot efficiency, epsilon sub Carnot, and we're going to define that as what you put in divided by what you get out. Sorry, I misspoke. What you get out by what you put in. So what do we get out? Work. And what do we put in?
Q hot.
Q hot. And because of the sign conventions, we have to put a minus. Just we'll put a minus here. Okay. So this is the definition of the Carnot efficiency. It's a very important efficiency. It's a very, very important efficiency. It's a starting point, even when you're looking at solar panels or people who work on solar stuff or anything like that. You always start as a Carnot, as a comparison for whatever you're making, because if it's, it has to be, we're approaching the Carnot. And so now if we know what W is just minus Q hot plus Q cold. Okay, and we divide this by Q hot. What we see, if you do the experiment, algebra here, is we get Q hot plus Q cold divided by Q hot, and that's just 1 plus Q cold over Q hot. This is our epsilon Carnot. Okay. It's very simple algebra. Maybe I went too fast, but go for it. Just do it on your own. I'll upload the discussion. The last thing, Q cold is negative. Remember, that's our sign convention. Q cold is coming out. Q cold is negative. And Q hot, since we're putting it in, is going to be positive. So the epsilon Carnot, this Carnot efficiency, is 1 plus QC, which is negative, divided by Q hot, which is positive. So that second term, that ratio of QC over QH, is going to be negative. It's going to be less than 0. What that means is that it's subtracted from 1. Okay, so your efficiency is 1 minus some number. And what this is saying is that even in the most ideal engine, which is this Carnot engine, you have ideal gas, you have reversible processes, right? You have nothing lost, supposedly. The epsilon, the efficiency of that engine, is less than 1. In the most ideal case. And that is depressing. Okay, thank you all for your attention and participation. I'm going to end the lecture there. Any comments, questions? This is a very profound result from thermodynamics, that you cannot have perfect efficiency. Amazingly profound. And now we'll see how entropy falls into that and relates to that. Okay, I'm going to encourage you to go to the discussion sessions. Tomorrow will be the exam. Just at 7 o'clock, log into this link via Zoom. Please, I hope everyone will be there with their cameras, and you will see that the exam will be accessible. And I said, just make pictures of your solutions and upload them. That will make it very simple. Okay, and don't be stressed out about it. 7 to 9, if it takes you longer, it's okay. We'll work it out. Just don't stress over it or anything like that. Okay. Any questions, comments? Thank you for your attention. I know I always talk more than I should. Have a great day. Have a great rest of the week, and good luck tomorrow.
Will we need calculators or
have your you will yes.
And are we allowed to have the equation book
yes
too?
Of course.
Okay.
Of course.
Thank you. Have a nice day.
Okay.
Thank you.
Yes, please try to be on Zoom. I know not everyone can be on Zoom. If you have to be working, I understand, but everyone else, if you can, please be on Zoom, okay? It's just this thing about ethics and, you know, the university and what have you. All right, thank you all very much. I appreciate your participation. The equation sheets is that's the handbook. So I have a question about the equations. There's a handbook that I mentioned at the beginning of the class, beginning of the course, and all of the equations are there. Okay, yeah, be on Zoom, Nathan, Nathaniel, Nate, yes.